All right, here's your second video for oxidation reduction, and we are going to focus on just assigning oxidation numbers and figuring out who's oxidized and who's reduced in a chemical reaction. You've got a little mnemonic device, and more often than not, I see these two terms confused in chemistry and in AP chemistry the same, oxidation reduction. Oxidation is a term that we use for any element that loses electrons in a chemical reaction. And reduction is any element that gains electrons. And you can probably see why students have a really hard time with this, because the reduction goes with the word gain. And if you just think about this, these were named way before they knew what was happening with electrons. These were named when they just were looking at oxygen being added to a compound or removed from a compound, hence the term oxidation. Now we know what happens to electrons, and there's a little bit of confusion here. But think about this. If you gain electrons, what happens to your charge? If you gain negative electrons, your charge goes down. It reduces. Your reduction here is reducing your charge. It's reducing your oxidation number. You can think about it that way. But I like to use a little mnemonic device here if you want to. If you can remember oil rig, you can keep track of these two. Oil rig will tell you oxidation involves loss, and the rig part, reduction, involves gain. And you want to have a mnemonic device keep track of this, because when we take the AP test in the spring, you might have a question that involves this. And it's a quick way to remember which one's which. It's really easy to get these confused. So have something like this. Or you could do Leo the lion. This is a common one too. Leo the lion says grr. Leo lion says grr. And the Leo part, losing electrons, is oxidation. Grr, gaining electrons, is reduction. Have some way to keep track of this because you're going to have to assign these terms for each element. So here's how we do it. If you're given a chemical equation, you want to assign oxidation numbers to every element in that reaction, both on the reactant side and on the product side. You're going to determine which one's oxidized by figuring out which element lost electrons. And if it lost electrons, I think you have this on your guide there. If you lose electrons, you get an increase oxidation number. That's what we're looking for, this element that increases oxidation number. And if you gain electrons, your oxidation number decreases, and you can write that in if you want to next to reduction. And that's how we determine which one's reduced. And so you've got two reactions down there. We'll just do each one of these individually, and you can see what's oxidized, what's reduced, and I'll show you a kind of way to diagram these out. So I want to go through my whole reaction and assign an oxidation number for every element. Mn, I don't have a rule for, but I do have a rule for oxygen, and this is a -2. It has to add up to the charge of the compound, which is a -1. And so I get a total of -8 for my oxygens on this side. And if I want to add up to -1, manganese has to be a +7. So my oxidation number is +7 for manganese. Chromium is already given me a charge here, and it's a monatomic ion. So this charge is the oxidation number for chromium. It's a +2. If I go to the right side of the compound, or the equation, to our products, manganese is neutral, and it's by itself. That's an elemental state, so it's a 0. Oxygen is a -2, and I have to use oxygen to figure out chromium again. So this is a -8 on this side, has to add up to a -2. So my chromium must be a +6 on this side. And if I connect these, here's what's happening. I'm looking for an element that changes. Oxygen doesn't. It starts out at -2 and ends as -2. No electrons are transferred to or from oxygen. But if you look at manganese, this is a great way to diagram them, connect them. Manganese went from a +7 to a 0. What does that mean? Is it gaining negative electrons or losing them? Well, if it's a +7 charge and it gets more negative, it's getting closer to 0, this has to gain electrons. And I'm going to write how many it gains. This gains 7 electrons. And if it's gaining electrons, we call that, if you go back to the mnemonic device, oil rig, the G in the rig is gaining electrons, that goes with your reduction. We would say that this element was reduced. Our other element that has a change, if you have one that changes, you have to have another one that changes, or you did something wrong. Because if something gains electrons, something has to give it up. And our chromium goes from a +2 to a +6. Well, that's losing electrons. It's getting more positive. And we would say that this lost 4 electrons. And we would say that chromium got oxidized, losing electrons. And that's what it looks like to diagram these reactions. Let's do it on our second one here. Now we're going to do the same thing, assign oxidation numbers. Nickel's by itself, it's neutral, so it has an oxidation number of 0. We also have that on the right side. I can quickly go to lead. Lead is neutral and it's by itself, elemental state 0. If you go to your lead nitrate, We don't know the charge of lead unless we look at nitrate, and this is an ionic compound. Nitrate has a -1 charge, and there's 2 of them, and so lead has to be a +2 charge, and that makes it a +2 oxidation number as well. Oxygen is a -2, and we already did nitrate. You can break it down again, go back to where we did that in notes, but your nitrogen is a +5. If we go to the right side, it's still nitrate over here, so still -2 and +5. Nothing's changed for nitrogen or oxygen, but the nickel now has a +2 oxidation state. And now I'm going to go and connect the things that changed. Nickel went from a 0 to a +2. And if it goes from a 0 to +2, it lost electrons. Oops. It lost 2 electrons. And if it loses electrons, it was oxidized. And our lead goes from a +2 to a 0. It gains electrons. It becomes more negative, and it gains 2 electrons. And we would say lead was reduced. And all we've done is assign oxidation numbers to figure out who's gaining, who's losing electrons, and why is this an oxidation reduction reaction. Before we leave these 2 reactions, though, let's go up and look at our first one again. Ask yourself this question: is this reaction balanced? And if you look at atoms, we have 1 manganese on both sides, we have 4 oxygens on both sides, and we have 1 chromium on both sides. You might be tempted to say this is balanced, but there's a problem with that. If we're gaining 7 electrons and only losing 4 electrons, there's 3 electrons difference here. And what happened to those 3 electrons, or where did they come from? Well, we're not balanced here. We might be balanced with atoms, but we're not balanced with charge. And the fastest way to see that in any chemical reaction is to just add up all of your charge on the left side. And if you add that up, this compound has a -1 charge, and this one has a +2 charge. And if we add up all of our charge on the left side here, -1 + 2, we get +1 on this side. And if I add up all my charge on this side, I get -2 on this side. And you'll notice the difference between these two is 3 electrons. There's my 3 electrons that I've already identified with my oxidation reduction reaction here. It's not balanced, and just the charges would tell me that. But if we break down our oxidation numbers, we can figure out exactly why it's not balanced. We don't have the right number of manganese and chromiums to get the electrons transferred correctly. And that's what the next video will do. It'll walk you through how to balance those. If you evaluate your second equation here and look at your electrons, we lose 2 and we gain 2, and so this one's balanced. It's balanced both in number of atoms and in charge, so we have the right number of electrons on both sides. I'll go through the last little bit of this here. Pause the video if you want to practice this, but you can go through these equations, assign oxidation numbers, and figure out if they're oxidation reduction reactions and who's oxidized and who's reduced. And I'll do that right here for you, and I'll do it quick for you. So oxygen is in elemental state, so it's 0. Our hydrogen is a +1. That's our rule for it. Carbon must be a -4, so that they add up to 0 for this compound. On the right side, our oxygen's a -2, and there's 2 of them, so we get a -4 from our oxygen. Carbon must be a +4, so that they add up to 0. Oxygen's a -2, hydrogen's a +1. And we want to ask ourselves, do we have oxidation reduction occurring here? Well, oxygen goes from a 0 to a -2. It gains electrons. And so these are gaining electrons. We do have oxidation reduction here. We gain 2 electrons for every oxygen. And if I connect my carbons, I go from -4 to +4. Well, that's going to lose, and we lost 8 electrons in this chemical reaction per carbon. And so this would be an oxidation reduction reaction. What was oxidized and what was reduced? Well, the one that's gained is reduced. So we get oxygen being reduced here. And the one that lost electrons was oxidized. Okay, if we go to our next one, sodium is a 0, chlorine's a 0. They're both in elemental state. Sodium's a +1 on this side, and chlorine's a -1 in ionic compound. We do have a transfer of electrons. I'll try to keep my color codes the same here. So we're going to figure out who gained electrons. That's our chlorine. It goes from a 0 to a -1, and we gain 1 electron, and that means chlorine was reduced. I'll just put an R for reduced here. And then for our sodium, it lost 1 electron, and it was oxidized. Okay. Our next reaction, copper is a 0. It's an elemental state. If you go to the right side, you have silver in elemental state as well. That's a 0. The silver is a +1. It's an ionic compound, and it's bound to nitrate. Nitrate we've already done a couple of times now. It's a -2 for oxygen and +5 for nitrogen. Copper is a +2 on this side. and our oxygen's a -2 and a +5 in nitrate again. And so we do have an oxidation reduction reaction. Copper goes from 0 to +2, and silver goes from +1 to 0. So we'll keep our color codes the same. Our blue is gaining electrons. So who gains electrons in this case? Silver does. It goes from a +1 to a 0. It gains 1 electron. And we would say that silver got reduced. So I'll put an R here and circle it. And then copper goes from a 0 to a +2. And so this lost 2 electrons. And we would say it's oxidized. This reaction's not balanced yet. Okay, if you go to your next one. This is a decomposition reaction. We have potassium with a +1 charge. It's in an ionic compound. Oxygen's a -2 charge. And they all have to add up to be neutral. If oxygen's -2 and there's 3 of them, I get -6 from my oxygen, a +1 from my potassium. Chlorine must be, what do we have here? Must be +5. 1 + 5 -6 gives me neutral, and that's what we want. So here's my oxidation numbers for each element. Don't do +6 for oxygen. Each atom in this compound of oxygen is a -2 for your oxidation state. +1 for potassium and a -1 for chlorine. It's an ionic compound, and oxygen's by itself, so it's a 0 at the end. Do we have oxidation reduction? We sure do. We have a change of charges here, or oxidation numbers. Oxygen goes from a -2 to a 0. Let's do it in the right order here. Chlorine, I have my blue, so chlorine's gaining electrons here. It goes from a +5 to a -1. It gains 6 electrons, and it was reduced. And then my green, who loses electrons? Oxygen does. It goes from a -2 to a 0. And so if we lose electrons, we're losing 2 here, and we would say it gets oxidized. Okay. We have 2 more reactions, and these are special cases. If you did this on your own and found something different than the other ones, that's good. I'll go through these. Hydrogen's a +1. Oxygen's a -2. You can do the math here and figure out that chlorine's a +7. Barium is a +2. Oxygen's a -2. Hydrogen's a +1. H2O2 on the product side, hydrogen's a +1. Oxygen's a -2. Barium's a +2. Oxygen's a -2. And chlorine is a +7. And if you compare all of your oxidation numbers, all of these oxidation numbers are the same before and after the reaction. This is not a redox reaction. And you'll find this for all double displacement reactions. None of them are redox reactions. So acid-base reactions that are double displacement are not redox, and neither are redox reactions that produce a solid. So our last one here, you should get the same thing. Sodium's a +1, chlorine's a -1, silver's a +1, oxygen's a -2, nitrogen, we've done this in nitrate a couple times now, is a +5. Sodium's a +1, oxygen's a -2, nitrogen and nitrate's +5. We have +1 and a -1. And if you compare all these, sodium before and after, chlorine before and after, for every single one of these, you have no change in oxidation numbers, and this is also not redox. Okay. Every other reaction is a redox reaction. And so if you look on your note guide, there's a set of 5 subcategories of redox reactions: synthesis, decomposition, combustion, and or single displacement. And you can assign these if you go back to the last slide. All of these are redox reactions. Your first one's a combustion reaction. Your second one's a synthesis reaction. Your third one's a single displacement reaction. Your fourth one's a decomposition reaction, and all of those have transfers of electrons. They're all subcategories of redox reactions. Your last 2 we've already talked about and described in class. Double displacement reactions that produce a solid are precipitation reactions, and a double displacement reaction between an acid and base that produces an ionic solid or an ionic compound in H2O are acid-base reactions, and neither one of these are oxidation reduction reactions. Okay. So that's how you identify your reactions, and I'll do one more video for balancing them.